The first method for numeric integration I'm going to discuss is useful when we have an analytic definition of our function and we want to find its definite integral. For any of the numeric techniques we're going to discuss, it's only going to be useful for finding definite integrals. None of these methods will be able to find the indefinite integral or find the antiderivative of our function. We need a lower bound and an upper bound in order to evaluate these. In particular, the method I'll discuss with MATLAB is going to use the integral, integral 2, or integral 3 methods, depending on how many dimensions or how many integrations we're taking. For single integrals, we'll use the integral command, double, integral 2, and triple integrals, we would use integral 3. Now, if you look in the MATLAB documentation or in the textbook, it might talk about methods called quad or quad L for numeric quadrature. These are older methods that MATLAB employed that it's phasing out. The integral methods are more robust and use many different numerical techniques in order to find your integral. Now, all the methods are going to work basically the same. We see that starting with the integral command, it takes 3 arguments. So the first one is we have at x, which is going to be what the variable is that we're going to integrate with respect to. Typically, I'll just call it x. And then we see fun of x, and that's going to be some function of one variable, x. Now we'll see how we use this in examples coming up, but this fun of x can be either an inline function, if it's something fairly straightforward, or it could be a separate M file that we can create that's going to give us some output. So in general, fun of x is just some function y of x. Then we have to give it its lower bound, a, and the upper bound of integration, b. The integral command and all of these are typically able to do improper integrals where we want to integrate from negative infinity to some value or some value to positive infinity or negative infinity to positive infinity. We can put any of those in as our lower bound if we wanted to. But in this class, we're typically going to be having non-infinite bounds on our integrals. Right. Integral 2 is going to work in a similar fashion. We have a function of 2 variables. This would be a double integral that we want to take. So if we want to find the volume of something, taking a step back, integral is going to find the area under a curve. Integral 2 is going to find the volume under a surface. So some function of 2 variables, so like z is a function of x and y, and then we have to give it the lower and upper bound for x and the lower and upper bound for y. And integral 3 is going to be a function of 3 variables, so something like q is a function of x, y, and z. We would have to define, again, as either an inline function or as a separate M file, and then lower and upper bounds on the x, the y, and the z. All 3 of these methods are pretty simple to employ. Now, the method MATLAB is going to use generally is called numeric quadrature, at least for the integral. Quadrature is used for functions of 1 variable, and cubature, they call it, for functions of 2 variables. We're finding the volume under a surface, like with integral 2. Now, there is a link here if you want to look into more how numerical quadrature works, some of the background programming for that. I'm not going to get into the numerical methods that MATLAB is employing, and for these integral 2, and 3, they can be multiple different methods that it's going to kind of adaptively use one or the other depending on how your function is defined. But for some just basic numerical quadrature, you can read up on that. Now, why would we want to use this quadrature technique if we have a well-defined function? Let's just go for easiness, call it f of x. Why would we want to integrate it numerically rather than integrating it by hand or analytically? So the advantages of using quadrature is that we can automate this process. So say we had to integrate a lot of different functions or the definition of our function is changing. For example, maybe in a looping environment. So we would not want to do that by hand because it's going to typically be slower than just letting the computer do it. So we can automate this, keep taking integrals of different functions, and getting definite integrals of functions and getting our answer. This is also useful when we have something that's defined by a function that we want to integrate, but finding its antiderivative could be very difficult by hand, very time-consuming, or it just might be impossible to do by hand. However, we might be able to find the definite integral, at least, by using these numerical techniques. Now, the drawbacks are we're going to have some error compared to if we did find the analytic antiderivative and evaluated it at the bounds. There's extra error introduced, which we do have some control over in the options of using integral, integral 2, etc. How much error we want to tolerate. I won't get into those details, but if you look in the help file, it's going to tell you all about how to control the tolerances. And the other drawback is we don't get that exact solution. We cannot find what the antiderivative of our function is. Now, if we had a case where we wanted to take the definite integral of the same function over and over and over again, maybe at different bounds, it might be useful to, if we can, find the antiderivative and then in MATLAB just evaluate that antiderivative at the upper and the lower bounds as they change. It's going to be a much faster process, and typically it's going to be a much more accurate process as well.